Let's dive into some content. Okay, so we want to talk about functions today. Actually, I want to say something before we get to the last question. I want to talk about functions today, and today we're going to see a lot of implications of being able to use first order functions and some, I'll say, neat features that we can use based on this understanding of how these first order functions work. This idea that a function is just a value, it's just an object, just like any other object in Scala, just like any other value in Scala, that can move around our code. It can be stored in variables, it can be used as arguments, it can be returned as values, which we'll see in the first example. And what does this help us with? And kind of one of the sad things about today's lecture is we won't get any more power that we didn't have before. There's nothing that after today you'd be like, I can do this now, now that I have this stuff. But what we will gain is another way of doing things that you can already do. We'll talk about the accumulator pattern. I'll reference that quite a bit from 1.15. And being able to do the same way in a much more compact way with, in my opinion at least, cleaner syntax, more compact syntax for sure, and being able to get more done with less typing. And I'd say to make your code more readable as well in the process. And as a bonus, it can help the compiler to optimize your code a bit more. So we won't be doing something more that we couldn't do before, but we will be doing something in debatable, I'll hedge my bets on this each time, debatably a better, more sophisticated approach to solving the same problems by leveraging first order functions. So with that, let's take a look at the lecture question. We want to write this function average in range. And this is a capital I, this is camel case, average in range. This is one of the cases where I'd recommend, I always recommend this, but especially in this case, cut and paste that into your code. Make sure you don't have any typos, no misspellings there. Because is that a 1, is that a capital I, is that a lowercase l? It's one of those characters that can really trip us up if we're not being careful. It's a capital I in this case. So this method takes a list of doubles as a parameter and returns a function, which is the first example we'll see. We'll see an example of returning a function. Returns a function that takes 2 doubles and returns a double. So we got a decent number of moving pieces here, a decent amount going on. We have 2 different parameter lists, 2 different return types, all in one function, all in one method. So takes a list of doubles, returns a function that takes 2 doubles and returns a double. And what this function does is takes a min and max value. The first parameter is a min value, the second parameter is a max value. And what it does is returns the average of all the points in the original list that are between those 2 values. And I say the endpoints are non-inclusive, exclude the endpoints, but these are doubles. I always feel weird saying that with doubles because we're always under the potential of truncation errors. So what does it mean for 2 doubles to be equal? What does it mean to be exactly on the endpoint of a double when we could have truncation errors changing what it means to be on the endpoint or not? So I feel a little weird saying that, but my tests will not get near the endpoints. And if your tests don't get near those endpoints either, we don't have to worry about that one of worrying about truncation errors and all those things. So, and then test this. The testing is an important aspect of this one, especially if you're doing, I guess for both of them, but genetic algorithm we'll use this quite a bit. I provide a good number of methods that return functions that you have to use to run your genetic algorithm and to test your genetic algorithm. So the testing, this being able to call this method that returns a function and then call that function, just going through the logistics of that and going through the syntax is good practice for what you have to do in your testing and genetic algorithm. So when I have this method that returns a cost function that takes in a list of points, just being able to work your way through that logistically, that's what the testing is going to get you practice with. And of course, writing the method itself, we have a method that returns a function. How is all this going to work? So any questions about the question itself? All right, let's talk about sorting one last time. Everybody's favorite topic. This is probably the last time I'll talk about sorting in lecture. I may refer to it in passing. Maybe we'll just have an application where we have to sort things. But this is the last time I'll really talk about it and shine a big light on it and say, this is sorting. So let's talk about one last thing that I kind of ignored last week, but one last thing that we still can't do with everything that we've seen so far. So we can sort based on a comparator, and we can run our comparison sorts, but our comparators have to take two values of the type that we're sorting and return a Boolean. That has to be the setup of a comparator. And if we're in a pure functional way of mindset where we're not allowing any state, and we have pure functions, which whatever the inputs are, if I call it with the same inputs multiple times, it's always going to return the same output. If we have pure functions and we're in this pure functional way of thinking with no mutable state and no state at all, how do we compare two values where the comparison depends on some other value somewhere in our program? How do we do that with a comparator that can only take the two things that we're comparing as its arguments? How do we do that? And the answer is going to be to write methods that return functions, and those functions have the input parameters baked into them or built in. So the example, to make this more concrete, I want to sort points, which are represented as physics vectors in the example we'll see. I have physics vectors. I want to sort them based on their distance to a reference vector. So I have some point in space and a list of points, and I want to sort this list of points based on their distance to this one point. Now the problem is I don't know what that point is until runtime. That point could be anything, I don't know where it's coming from, but I have some point that I'm not going to get until my program's run, so I can't hard code this in my code. If it's I know it's always going to be the origin, something like that, I could just code that. But if I have a reference point that I don't know what it is until my data is about to be sorted, how do I do that? Now with object-oriented programming, with that mindset, we just throw that in a state variable. We create our comparator as a class, create an object of that type, set the state variable, and then give that comparator method to the sorting method. Now that method has access to the attached object state, and it can access that state variable, and we can get that done with a method. But how do we get that done with a function? When we want the same behavior, we want to be able to do everything that we could do before. If we're getting more restrictive in what we can do, what's the point? Why are we even talking about this? So we want to be able to do everything that we could do. So how do we handle this situation here? And of course the answer is on the screen, but let's talk about that and what that looks like. So if we want to sort by that reference point, we can write a method that returns a function, and that returned function is going to have the definition that we need. It's going to have the input types and the output type that we need for a comparator. So this is going to return our comparator that compares two physics vectors and returns a Boolean to say how they should be ordered. So that returned function is in the exact format that we need for our comparator. That is going to be our comparator, but we get to bake in this extra vector into that comparator. Because really what we would want is a comparator that takes 3 physics vectors, and that third physics vector is the reference vector. But guess what? When we go to our merge sort code that takes a comparator that only takes 2 values, merge sort is going to say, hey, this isn't what a comparator is. I can't work with this. I don't know what this is. That merge sort code that we wrote, it needs to just take 2 parameters. So we're going to take in the reference point as an argument to the method, and we're going to write a function with that reference point built right into it. So this function, this whole body of the method is the function definition. So this is what's returned. We're going to compute the distance of each vector to the reference point, and then use the less than operator. So we're going to sort an increasing distance from that reference point. Now when this function is returned, it's in the format that we need, but has this reference point built right into it. And we can do this at runtime. So we call this method with any reference point that we have, and we can get that functionality whenever we need it. This way, we have a comparator, which is a pure function. Given two vectors, this is always going to return the same value. Two vectors, no matter how many times I call this, it's always either going to return true or always going to return false. That reference point cannot change. So I don't have to worry about the behavior of my comparator changing because someone somewhere else in my code decided to change the state of that object that my comparator had, change that reference point. I don't have to worry about that happening mid-sort. It's not going to happen. This is a pure function. It's always going to have the same output on the same inputs, so long as my physics vectors are immutable. As long as I'm using veils on my physics vector. So the physics vectors from Gen Algo, not the physics vectors from the physics engine where they were immutable. So as long as these are immutable, we're always going to get the same output here. And furthermore, this method itself is pure. Whenever we give this method a reference point, it's always going to return a function with the same behavior. So I have a pure method that's creating pure functions. Nothing's relying on state here. I don't have to worry about the state of my program affecting the behavior of this comparator. And that's something I haven't really been mentioning, but a big advantage to this functional programming way of thinking, this idea of no state in our programs, makes things a lot easier to test. If we have a pure function, okay, give it some inputs, check its outputs, make sure everything's behaving the way it should be, test it. Not too hard to test that thing, compared to testing a method that can depend on state. So if I have a method that depends on state, I have a whole new dimension to my testing. Okay, here's my inputs, here's my outputs, let's make sure it all works. Okay, now let's change the state of this object. Now I expect this input-output behavior. Let's run all those tests, make sure I get what I want. Let's change the state again to some other state, run it again. I have a whole new dimension here. I have basically two-dimensional testing. I have to vary the inputs, I have to vary the state, and make sure I always get the right output based on that combination of input and state. We don't have that with pure functions. We test the function once. Input-output behavior is good. We're good. So it's one big advantage that we get with all this immutability, all this functional programming. Things should be easier to test. We test each function individually, and it's a bit easier to test that thing. And then to use this, finally, when we call our merge sort and we're ready to sort some points based on their distance to a reference point, I'll call the distance comparator method, give it the reference point that I want to sort around. That's going to return this function in the comparator format, and that's my comparator to merge sort. So I'm calling a method to sort this data structure, and I'm calling another method that returns a function which is going to be my comparator for this sort. So that method is generating my comparator at runtime as opposed to at compile time. Depending on compile time and then depending on state, it's being generated at runtime and then not depending on any state. Okay, any questions on returning functions? So the next part of the rest of the lecture, I'm just going to go rapid fire through a lot of implications of first order functions, which is going to be a lot of data structure methods built into Scala that we get to use based on that understanding. Yes, you should account for duplicates in the lecture question. So if I have so for the lecture question, if I have a data structure, my input is 1, 2, 2, 3, 3, and 4, and my endpoints are 1.5 and 3.5, my output should be, oh, that's a bad example. My output should be 2.5, forgot what I said. That's a bad example because remove duplicates would be the same answer. But if it's 0, 1, 1, 2, 3, and my endpoints are 0.5 and 2.5, my average should be 1.3333 or 1.66666, repeating. Yeah, the input list can have duplicates, and that's fine, that's acceptable. Any other questions before we dive into some functions? Let's dive in. All right. So I linked to some Scala documentation that goes over a bunch of these. The documentation calls them collection methods, which I think I have that. There are 2 lectures that's finally bugged me enough to change it. Collection methods. Maybe they do call them collections methods. I don't know. But it doesn't matter. It doesn't change the meaning. Collection methods. So when we have a data structure, there are a lot of methods that we can call in that data structure that take functions as their arguments and help us compact our code, help us clean up our code, and just give us really an alternative way of doing things. Unless your professor takes away var immutability, then this is what we're left with to be able to work with data structures. So this is a different approach, it's a different mindset, it's a different paradigm, this functional paradigm, this functional way of thinking. And I, of course, I've said this a bunch, but I'm pushing you down that, kind of forcing you to get your hands on this and get an idea of what this paradigm is. And I do that not just to be like, to force you to see it, but this is something that you're almost certainly going to see throughout your careers. Somebody on your team is going to be that functional programmer person who loves all these methods, and you're going to see them in your code. You're going to see them in documentation that you read. You're going to see them in, for what it's worth, future classes. You're going to see this throughout your career. It's going to come up from time to time. You got to be familiar with what these things are. And personally, I think it's a cleaner, more elegant way of coding that I think a lot of you will, once you have to get used to this, you might not go back to the old 115 style of writing. But anyway, with that introduction, let's just dive into these and see what they are. So first one, for each. If I have a data structure, here are lists. We'll see lists today. If I want to call a function on each element of a list, I'm going to use for each. So I have my words, just some simple data structure, words.forEach, and then give it a function, technically a method in this case, println. And it's going to call println on each of those elements. So this is not that useful if you're fully in the functional programming mindset, but it's a really simple first example. Plus I'll use this in the other examples just to print things to the screen, just so we can see what each one of these methods is doing. But if you're in the full immutability mindset, this one isn't very useful because println for each is going to return unit, and it takes a function that returns unit. There's no return value. You're strictly calling for each on a function that you're calling strictly for the side effects. In this case, my side effect is changing the state of the screen. That's what I want to do here. I'm not concerned with any return values or any data processing or anything. Strictly the side effects printing it to the screen. So not too useful in a pure functional paradigm. Pure functional programming doesn't have much use for each. But we can get used to this syntax. We have a method that's taken a function, and that function is going to be applied to all the elements of our data structure. That's going to be the theme of all these methods. Filter is going to take a function that takes the type of the elements of the data structure as its parameter and return a Boolean. And it's going to return a data structure containing only the elements of that data structure for which this function returns true. So I'm going to filter all of my data based on this function that returns a Boolean, and then just get those filtered elements. I'm taking all of the strings with length greater than 3 in this case, and I'm going to use this underscore syntax throughout the day. And I will show one expanded function later today with the full syntax. And I'll talk about this more when we get to that slide. But I will use the underscore syntax. So a reminder, this is a shorthand way of defining a function in Scala. This is pretty specific to Scala, this syntax. But this means instead of saying s of type string and then equals greater than, like that big arrow, then the body of the function being s.length greater than 3, instead of writing out the entire function with the parameter list and the body of the function, this is the shorthand that says, look at Scala can infer the type of the input. It's expecting an input of type string. There's only one input, so I'm just going to put an underscore here in place of the name of the input. So this would be the same as saying string s of type string, s.length. This is in place of the name of the single input parameter. And you just say underscore and then treat that as my input to this function. So a little shorthand, I'm only specifying the body of the function, and the name of the input is going to be underscore, and the type of the input is inferred based on filter expecting a function that takes the type parameter of this data structure. Let's keep moving. Actually, I want to talk about this here before we keep going down here. And this is where you can start to see that, well, we're not getting any more power here. This is something you could do in 1.15. You would say var filtered words of type list of string equals new list, an empty list. Iterate over these words, say for word in words. If word.length greater than 3, append that word to the filtered words list, and then by the end of that loop, filtered words has everything I have in it. That's certainly something within your capability. Of course, I had to use a var to get that done, so I'm pushing you towards this way of approaching it. But it's something you could do before. But with this approach, what we're doing is instead of explaining to the computer how we're going to accomplish something, hey, Scala, compiler, create an empty list, iterate over this data structure. If this Boolean is true, execute this code which appends that value to this new list that I created. Do that, iterate through that loop, and then take this data and then print it to the screen or whatever we're doing after that, return it. Instead of explaining to the computer how we're going to do something, we're describing what we want to get done. Take these words and filter them based on this condition. It's much more descriptive, it's much more compact, and it's, once you get used to it, in my opinion at least, easier to read. Words, filter, based on this filter. I don't have to look through your loop and say, notice the accumulator pattern, recognize that and everything. Words, filter, based on this condition. I got it, I know what's going on there. Very compact. It replaces an entire loop and an iteration and accumulator variable. And besides the advantage of just being more compact code, it reads more like an English sentence, but it also helps with the compiler. If I'm setting this up the way I just walked through it, where I have filtered words initialized to an empty list and then appending to the end of it, well, append for a list, and I'm using immutable lists here, those append operations are very expensive. Those are very inefficient. If I say, look at compiler, this is what I want to do, now the compiler can optimize that for me, and it's not going to do something silly like appending to the end of an immutable list, which is a crazy expensive operation. It actually copies the entire list every time I call that. Instead of doing something like that, this is going to take code written by teams of engineers who spent decades optimizing everything and take that most optimal solution that they've found, apply that to our data structure, take our function, and do the best thing that they can do. They've said, okay, We need to filter a data structure based on some function that returns a Boolean. What's the best way to do that? Similar to the Tim sort, I don't think this is a lecture, we busted into that, but the built-in Scala sorting method, the algorithm is called Tim sort. It's a modification of merge sort. That's very optimized. They've spent a long time optimizing that code. And we want to leverage that optimization. We wouldn't write our own merge sort. We wouldn't take the merge sort that I wrote and use that in our production code. We're going to use that highly optimized Tim sort that's built into the language, built into the standard library, give it our comparator and let it do the work. We're doing the same thing here. I want to filter based on this function. Let that optimized, highly optimized code work for you. And you can have much more efficient programs because the standard library can work for you and the compiler can work for you. The compiler can start finding optimizations that you might not have found also. So instead of being bogged down with all those little implementation details, just tell the language and tell the compiler, I want to filter based on this function and let all that other work not go to waste. Leverage all that other work that's been done for you, that's provided for you for free, and take advantage of it. Get your optimized code without having to optimize it all yourself. All right, so with that, let's plow through a few more of these. Map. This is similar to last Monday's lecture question. I referenced it on last Friday as well. Map is going to be similar to that. I have a data structure. I want to apply a function to each element of that data structure and return a new data structure based on the output of that function, the return values of that function when it's called on each element. So if I have this list of numbers and I want a new list with all these numbers squared, numbers.map, and then some function, again using that underscore syntax, some function, in this case it's going to take each element and square it. Math.pow, each element, square, I get a new list of doubles with all those values squared. So it's going to take a function, call this function on each element, accumulate that into a new list, and then I'm just printing that list to the screen. Map can also change the types. So the last example, so map takes two type parameters. The last example, both those type parameters were doubles. I gave it a function that took a double and returned a double, but we can also change the types we can change the type parameter of the list using the map function. So if I have these strings and I want to turn this into a list of ints with all the lengths of those strings or whatever transformation you want to do to this data, map, just give it a function where the input type of course has to match the type of the list that you're calling it on. So this input is going to be a string, and I'm using underscore, so that was able to be inferred by Scala. Scala knows that words is a list of strings. You're calling map. Map expects a function that takes a string, so underscore is of type string. But .length returns an int. So since it sees that it gets a function from string to int, the map method knows that its second type parameter must be int. So now it's going to return a list of ints. I get that list of ints, and it has, of course, the data that I expected there to be in there. So we can change that type just by the return type of the function that we give the map method. So this, if you have data of one type and you need to transform that into data of some other type, map is where you're looking. Even if the types are different, you have some inputs, maybe you have inputs that are potential solutions in the genetic algorithm, and you need to output, you need to transform that into something containing the cost information of those, which I recommend creating a new class to store that. But besides what we're talking about, something where you would have to take in the potential solutions, map them onto something that can be sorted by the output. You know what? Let me not go down that road. I think I'm giving a bad hint on that anyway. But you want to do something. Whenever you have data of one type, you need to transform that into a data structure of some different type, do some sort of processing to it, whatever it is. Call map. This is the way you can do it. specifically when var is banned, but if you're thinking in this functional programming way of thinking, I have a method that takes a function and does what I need it to do. Very compact code. Look how much work is done just with this little amount of code right here. And how much code that would take without doing something like this. It would take quite a bit more. Yield we saw on Friday. This actually does the same thing that map does. So yield, we set up our for loop just like we would any other for loop, but right before the body of the loop we put this keyword yield. That's going to tell Scala, hey, this loop, I don't just want to execute the body of this loop for each element. I want to collect the results into a data structure. And then I want you to return that data structure. So the body of the loop, whatever the last expression to be evaluated in the body of that loop is, those values are going to be accumulated for each iteration of the loop. Those are all going to be collected and thrown into a data structure. And that data structure is what this entire loop resolves to, right from the for all the way to the end of the body of the loop. This whole thing resolves to a data structure containing those values, those last expressions that were evaluated in the body of each iteration of the loop. So in this case, we can think of the loop body as somewhat of a method call, where a method returns the last expression that's evaluated. We can kind of think of this being a method that's called on each of the elements of the data structure, and then whatever each method call resolves to, collect all those values into a data structure, and then return that data structure. So we get all that with this by putting this yield keyword here. So it's the same thing as map. If we called map and use this as the function that we were giving it, that we're giving the map, we're going to get that same behavior out of yield. It's just a different way of setting it up, different syntax. And for me, for my money, this I would use map. I would say numbers.map, map.pow like we did on the previous slide. But my preference, it's whatever you want to do. My preference is when I don't already have a data structure with data in it, that's just for whatever reason, something with me. That's when I like to use yield. When I, for example, am iterating over the numbers 1 to 5, I would like to do yield here and then yield those results into a new data structure that I'm creating on the fly. Like that. One thing with yield is it's going to try to match the type of the data structure which you're iterating over. So here, in the previous slide, I was iterating over a list. So no problem, I'm going to get a list. I'm going to store that in a list, a variable of type list. But here, I'm iterating over a range, the range 1 to 5. So yield is going to try to put the results in a range. It's not going to have much luck with that. So it's going to put all of this data into some default data structure. I'm pretty sure this would be a vector in this case. It's going to put all these values into a vector, and that's going to be the data structure that this for loop resolves to. But that's not what I want here. I want a list. So if you don't want the default value, for whatever reason, even if that reason is the lecture question asked me to return a list, if you need this in a list, what I'm going to do is put parentheses around this entire thing. So this for loop, this entire thing resolves to that data structure. I'm going to put parentheses around this entire thing. So everything inside the parentheses is my data structure. And without the parentheses, by the way, you'll get an error. Scala won't know what toList is being applied to. But I'm going to put these parentheses around this entire thing. That entire thing resolves to a data structure. And then I'm going to call .toList on that data structure. So whatever it was, if I don't want to remember what Scala defaults to, what that data structure type is going to be, we know the type parameter is going to be double, but I don't know the type of the data structure. It's not going to be a list, in this case a vector. I don't care. Convert it to a list for me, and then I'm going to work with it as a list. So convert this entire thing to a list. Now I can work with it as a list, and then do what we've been doing before. Yield, oh, I didn't mention this one. Yield, another preference thing. I like yield when I have more complex functions. If I have a lot of functionality that I have to implement, I'll typically use yield instead of mat. Again, preference, yield or mat, choose whatever you like. Choose what you like. Any questions so far? Okay. Everyone getting comfortable with the syntax? Reduce, let's see, start seeing a little more power, a little more complexity here. And this is where the one time I'm going to expand the function that we're using. Reduce is going to take a function that takes two inputs of the type that we're iterating over and returns a value of that same type. And it's going to apply that function to every element in the list such that it'll compress that whole, reduce that whole list into a single value. So I'm going to take this function and apply it to every element to get a single value out of this list based on that function. And I have my, words. So I have my function expanded into the old-fashioned, and I say old-fashioned lightly, it was just last week, but the old way of writing the full function definition. So I'm defining a function that takes two doubles, which I'm naming a and b, and the body of this function takes a and adds b squared to it. So what I want to compute ultimately is the sum of squares of these values, which I get down here, and I want to do it with this function. I'm going to assign that to a variable of type double, double to double, name it sum squares, and call numbers.reduce sum squares. So reduce is going to take a function in this format where the first parameter is going to be the accumulator variable, much like the accumulator from the accumulator pattern in 115, is going to be the accumulator variable, and the second parameter is going to be the elements of my data structure, one at a time. So the accumulator pattern, what reduce does is first sets the accumulator to whatever 0 is for the type that you give it. So here, doubles, so I'm going to get 0.0. That's going to be my initial accumulator variable. And then this function is going to be called on the first element of my data structure. So I'm going to get a equals 0, initialized. B, the first call, B is going to be the first element of my data structure. I'm going to take 1 squared, add it to 0, and get 1. Then reduce moves on to the next element of my data structure, remembering and passing along that accumulator variable to the next call of this function. A is going to be 1. B is going to be the second element of my data structure. I get 2 squared, 4 plus 1, 5. Next time this is called, A is going to be 5. B is going to be the next element of my data structure. I get 5 plus 9. The next iteration, A is 14. B is 4. I get my 14 plus 16. 30 is A. 5. B is 5. I get 30 plus 25. I ultimately get my 55. So I reduce this entire list down to a single value based on the function that I give it. But it was very important that I get the order of my parameters right. The first one's the accumulator, the second one is whatever data element I'm looking at. So I got to make sure that I keep those straight. A is the accumulator. I just want to add to the accumulator the square of the current element that I'm looking at. And we want to be aware of the order of our data too. For this one, my data, this function is all symmetrical. I could run this backwards through my list. I'll get the same exact value. But we do want to be aware of that. By default, all these methods, reduce, fold, we'll see next, they're going to work from left to right. Or rather, they're going to start with the first element of the data structure, then iterate through forward. If we want to go backwards, there are different versions of each one of these methods. I could do reduce right, and that's going to go backwards from right to left through my data structure. That by default, we're using reduce left. Reduce all reduce does is calls reduce left, and reduce left does the work. So by default, we're using the left versions of these. So I used the expanded way of writing this function, and then gave the function variable storing that function. But we can actually use the underscore syntax for this one too. So we can use this underscore syntax even when we have two parameters. But again, the order is significantly important here. The first underscore that appears in the definition of my function is going to be the first parameter of that function, and the second underscore is going to be the second parameter. So I have to be very careful that the first underscore that appears in this definition is what I expect to be the accumulator variable, and the second one is what I expect to be my current data element that I'm looking at. So the order is important here, and this is Scala-specific syntax. Scala, the engineers decided that this is how they're going to do it. It's just the order in which they appear is the order of the parameter list, which means that we can't use a parameter more than once. If we need a parameter more than once, if we need to use it more than once, we can't use this underscore shortcut. Because if you have three underscores in your function, if I have three underscores in this function, how does Scala know if I'm trying to use the first parameter twice, or if I'm using the second parameter twice, or did I actually mean a function that takes three parameters? Scala's going to assume that I meant a function that takes three parameters in that case. So this is the way it's set up. That's the way we'll use it if we want to use this shorthand. But we can compact that quite a bit. We can see, again, how expressive this is. This list of numbers, reduce it based on accumulating, summing up all of the squares of these elements. It takes a while to get used to the syntax, but once you do, that reads pretty much like an English sentence. Can you use map inside a yield? If you mean iterating over a map, yeah, you can iterate over a map and call yield. If you mean creating a map with yield, I don't know, I'm not 100% off the top of my head, but I believe if you, how would you do that? I believe if you return the key and value pairs in the loop, I'm not 100% on that, I'd have to look it up. But I believe you can yield a map, I just don't know the syntax off the top of my head. I can guess, but I'd just be speculating. But you can certainly iterate over a map and use yield, which the syntax might be a little cleaner than using map in that case. That might be a case where I'd want to use yield if I'm iterating over a map. Yeah. Any other questions on reduce? Yeah.
So during the time of doing rhyming dictionary and along with that in the recursion, I have used this underscore, but it had different meanings with that. So just like for doing the question when I was searching online, like how to put values into recursion into a list and how to do with cases. So over the web, I found out this underscore is used for default and also for if during the time of rhyming dictionary, it was to remove all the digits from the videos. So I want to understand how things are working with this.
So the underscore character in Scala does have different meanings depending on what we're doing. If this is the meaning of underscore specifically when we have what we call anonymous functions. These are functions that we're never naming. Underscore has this specific behavior. In other places, underscore is usually the, like an asterisk in other language is the wildcard operator, which just means anything. So if I say import physics dot underscore, it's going to import every class and object from the physics package, for example. If we have, like when we did overrode the equals method, and we have the switch, the match case statement, like you're referring to, the underscore means anything else. So you would say match case, if it's this type, do this. If it's this type, do this. And then underscore, case underscore, else, do whatever else. Handle the default operation. So it has different meaning depending on the application, depending on specifically what we're doing at that time, where the underscore appears. So it's an overloaded character. All right, so reduce is cool and all, but reduce always initialize the accumulator to 0. But what if I want to do something like multiply all the elements of a list together? An accumulator initialized at 0 doesn't do me much good there, because guess what? I'm always going to get a result of 0. I just can't do this with reduce. So fold is going to give us 2 extra pieces of functionality. One, it's going to let us initialize an accumulator variable. Here, I want to initialize this to 1. I want to initialize to the multiplicative identity, so when I start multiplying these things together, I'm not just always getting 0. And it does that by being a method that returns a function. So fold is a method that takes that initial value and returns a function with the functionality that we expect, mostly the reduced functionality, but with that initial value baked into it. Similar to what we saw at the first example with the comparator, is going to return a function with this initial value baked in, and then we're going to call that function with a function that we're defining on how to fold these things together. So we get quite a bit going on one line. We're calling a method that returns a function, then immediately calling that function with another function as its argument. So that's why you see this double parenthesis sign. This isn't just a weird way of sneaking in one extra parameter. Actually, it kind of is. But what it's actually doing is returning a function, and then we're calling that function right away without storing that function in a variable in the meantime. Calling a method, returns a function, call that function with a function as the parameter. And then I'm just going to multiply accumulator multiplied by the current element I'm looking at. We're going to get all these values multiplied together. We would also use fold if we're changing the type as we're accumulating. If the accumulator variable is a different type than the data that we're iterating over, then we would also use fold. Here I'm returning doubles, so I'm not really taking advantage of that. But in the next example, if we go to our polynomial code, this is part of the handout for genetic algorithm. These polynomials, I use a few of these methods. Actually, a lot of the handout code for both assignments. You can see lots of examples of where I use this stuff. As I was getting all the vars out of my handout code. Evaluating a polynomial I can do using a reduce. And I just want to walk through this to see how we can use reduce to get some things done, to get this done in this case. And I used the expanded terms. I expanded this a little bit just to make it, I wanted to name my variables, so I expanded this a little more than I normally would. Oh, it is 450. Anyway, my accumulator, I'm going to multiply that by x and add the coefficient. So if I have a polynomial in this format, I have 1.5. It's going to be my initial coefficient. You know what? I don't want to, I only got negative times, so let's check out this other one. Fold left, I want to use fold because I'm accumulating. What this is returning the cost function for a polynomial given a certain set of points. So how well does a polynomial fit these points? We have to return a function because our genetic algorithm is expecting one potential solution, polynomial in this case, and then returning a cost. But I want these points baked into that function. So I'm going to take in that list of points, and I want to accumulate the total distance of those points, the sum of the square distances in this case, and accumulate to a double, but I want to iterate over points. So I have to use fold left. I have to give it some initial value if I want to use fold, and then for each point, accumulate that distance and keep summing up the squared difference of that distance. and normalize by the number of points in the end, so I'm not penalized for having more points. And with that, yeah, we're out of time. So I'll see you everyone Wednesday.